next presenter from ETH Zurich, Faveo Horold.
All right, thank you. So I'll be talking about unlocking low precision floating point for scientific computing. Just off the bat, a lot of this is based on our SC paper from last year. So yeah, big thanks to my co-authors. And also shout out to the Riken team because all of this stuff ran on their cluster, so that was really helpful. So I'll dive right into this with motivating a few points. First of all, why do I want to talk about low precision floating point for scientific simulations? First of all, there's a preprint from Jack Dongaro where he says essentially artificial intelligence, particularly deep learning, has profoundly impacted floating point computation, and as a result, reduced precision floating point types have become increasingly popular in AI applications. And right away, we can see this in NVIDIA hardware, right? So we have Hopper GPUs boasting with like 30 teraflops of raw FP64 performance, and then we look at Blackwell, and this goes down to 1.3 teraflops. And of course, there's a lot more factors that flow into this. You have increased bandwidth, which again benefits scientific simulations because a lot of them are bandwidth limited. And there's also other factors, but it's quite clear that FP64 is kind of moving into the background in the face of AI, benefiting much more from low precision operations. I was going to say a similar thing for AMD, and then I had a really interesting discussion yesterday with Bob and Samuel and a few others from AMD. And AMD is not as much moving this into the background, but I think what they are doing still supports the argument I want to make. And there's this interview with Nick Malaya on HPC Wire, and I think he summarizes this quite nicely. So NVIDIA is really boasting or like pushing towards using Ozaki schemes to emulate FP64. But this interview kind of summarizes why this might be a problem or why this might not be sufficient for scientific simulations. So first of all, Ozaki schemes are not IEEE compliant, so that means you will not get subnormal numbers or subnormal behavior. You will not get infinites or nans, and this can be a problem if your scientific application relies on that. They deviate from true FP64, so they are very accurate. They have similar accuracy to FP64, but in the end, the results might be different. And in some cases, if you have specific matrices that are conditioned in that way, then this will be a problem when the Ozaki scheme deviates from that. And then finally, Ozaki schemes are for DGEM, so they're for matrix-matrix multiplications, and scientific simulations are not all just matrix-matrix multiplications. There's vector operations in there, and there's a lot of things that are not linear algebra at all. So it takes a bit more work to do that with, without using FP64. And then, yeah, for the numbers, yeah, we can see that here AMD might be pushing towards something like 200 teraflops. I could not find official numbers. I don't think they're out yet, but there's some fairly trustworthy estimates, I would say. So we still see an increase here. But like I said, I still think that we need to consider low precision floating point simply because these newer GPUs will still provide all of these low precision capabilities. The performance is a lot higher. And if we can make use of that in scientific applications, then maybe we can break some more barriers. So I've motivated why I want to talk about low precision floating point. I also need to motivate why scientific simulations are still relevant already, although we've also heard this this morning from, I think, both from Thomas Schultes that things like data assimilation in weather and climate simulations are still very important to support training data for AI models. And also Eric Lindahl, kind of the takeaway I took from his talk is that sure, AI models have amazing speedups and can do a lot of amazing work. But maybe the best way to move forward is to kind of have hybrid simulations where one supports the other. And in this case, you still need scientific simulations, which currently rely on FP64. And then also, again, to cite some papers here, there's a Nature paper where they say, well, physics-based models will remain vital simply because the physics generalizes in ways that are designed to fill in sparse observations. And the point is that AI models cannot generalize in this way. There's this idea of the black swan event. So if you've always seen white swans, you have a lake, have some swans on them, they're white. Why would there be black swans? Well, this was never in the data that you saw, so why would you predict that there is such a thing as a black swan? But in climate science and climate simulations and weather simulations, we have this effect of ever stronger extreme either heat events or precipitation events, which kind of follow this kind of black swan idea, which is simply that the conditions are changing due to climate change, so we get these more extreme events that we haven't seen before. And the second paper that I've listed down here actually talks about how classical physics-based simulations are able to predict these events in the case that the initial conditions and boundary conditions are right, which is what we get due to climate change, and they outperform AI models in predicting these kinds of events. Yes, so I've motivated why I want to talk about low precision flowing point and why I want to talk about scientific simulations. So the next question is, well, how do we actually use low precision floating point? And specifically, how do we use it in cases where we don't already have kind of theory developed for linear algebra applications? How do we go outside of those spaces? So for the paper, we decided to keep it simple. Domain scientists do mostly know what they're doing. Most of the time know what they're doing. And the point here is, well, the domain scientists will know their application best. And in this case, we have some kind of code that does adaptive mesh refinement. So we have kind of 3 levels of cell sizes here. So we have the coarsest cells, which are marked by number 3, then something in between number 2, and then we have the finest cells at number 1, which kind of really cover the areas of the domain where the interesting physics are happening. So in this case, we have some kind of expanding shock wave, and of course, around that shock wave, we will want the finest resolution, because this is where the most interesting things are happening. And their idea, this domain scientist hypothesis is, well, since we already have this adaptive mesh refinement, maybe we can just get away with truncating everything that isn't the finest cells, and that's going to be fine. We don't care if number 2 and number 3 are calculated at low precision, because there's nothing interesting happening there anyway. So what we want to do is to test their hypothesis. So how do we do that? We just want to truncate some things. Clearly, we're not going to do this, so of course we could just find all C++ files and then do some sed and bash magic and just replace double with float. No, we want to do something more sophisticated. And the reason is, first of all, we want to try different formats, and there's an explosion of formats. You can even have the same bit width, but have different sizes of exponent mantissa, so we want to be flexible in that regard. Second of all, we don't want to truncate everything. Maybe it turns out, well, okay, function foo and baz are interesting, but bar we already know is not that important for performance. It's fine if we emulate FP64 there, and it might cause trouble anyway, so we want to leave that out. And then third is, of course, this idea from the domain scientist. We might want to truncate on a dynamic basis, so whenever bar is executed in this finest domain, then we want to run it at full precision. But whenever, for example, maybe it's larger or equal than 3, then it's fine to truncate it. And this is specifically what we tested. So our tool is called Raptor. It's an LLVM-based tool for precision experimentation with a focus specifically on scientific code. It supports this full range of FP formats. The idea is to make it as easy to use as possible, so you don't need to rewrite a bunch of code to try this out in your scientific application. We wanted to have as fine of or granular of a control over truncation as possible. So you want to be able to specify only specific functions that should get truncated, but within those functions, you might also want to take out specific operations or specific parts of that function where you already know that using low precision is going to be a problem. And then finally, we essentially support all languages that LLVM supports, and also CPU and GPU, again, through LLVM. And also just to kind of quickly compare this with other tools, I don't want to spend too much time on this, but on the left, we can truncate the full application, which is useful to just do an initial test and see if this is working at all, if your build setup is working at all. We can truncate on a dynamic basis, which we will use to test the domain scientist's hypothesis and see if truncating in different parts of the domain will help at all. Support a bunch of formats. We can support truncating only specific functions or only specific operations. We can also track errors throughout the application. And it works on non-differentiable code. And there's more details about this in the paper, or we can talk later if you're interested. Yes, and then also for the Raptor internals, I will go a bit more quick here because this was already covered in the conference presentation. And frankly, I'm also not the expert on compiler internals, so my knowledge is limited in this area. But the point is you have a Raptor pass which operates in the linker stage of LLVM. So at this stage, it will be able to see which functions are calling which other functions, and thus it can really make sure that the entire function call graph is covered. And then there's a runtime which lets you kind of implement all these measurements for different metrics that you might be interested in when you start truncating. So the simplest mode that we can use Raptor in is this op mode. And in this case, on the left, you can see we have some kind of fadd operation, then a print, and an fmol. And all that op mode does is truncate before this addition, and then perform that addition in low precision, and then expand back to FP64 and store the FP64 kind of expanded result back in this %d register. And the benefit of doing this is that the truncated operations happen transparently. So this print operation, or any other function where Raptor does not have access to the source code, where we cannot really truncate this, will be able to use this FP64 variable transparently without the truncation process breaking anything. Yes, so in this case, we just go to FP32, so it's a precision that's available in hardware. We can also use MPFR, which is this library for multi-precision floating point computations. We can use that to go to any precision. So we rely on that to provide this arbitrary precision support. And as a note, this is unavailable on GPUs, but as far as I know, there's no real technical reason for this. It's just because perhaps no one has really needed this so far. And I would argue it's also not a super high priority because GPUs already have so many precisions available. So, but if someone is willing to port this, then I would be very happy to integrate it into Raptor as well. Yes, and then finally, I already mentioned this. If you have a function that is called transitively, so you have foo, which calls bar inside, and you decide to truncate foo, then Raptor will be able to detect that and also truncate bar for you. So the entire call graph gets truncated. So let's look at the actual results. So the first one you've already seen, it's this set of blast wave. So it's essentially an explosion. And all the interesting stuff is happening around this shock wave. So you can see around the center we have the very fine grid cells, and then it gets coarser towards the edges. And then what we can do is kind of decide where we want to truncate. So in this M-0 panel, you can look at this highlighted line and essentially see that on the right we have full FP64, so 52 bits of mantissa, and then decreased precision towards the left. And as you decrease the precision, your accuracy decreases and your error increases. And as soon as you get to like FP16, you're already at like 10 to the -2 error. And of course, it explodes as you go to ridiculous tiny precisions like 4-bit mantissa. And this is if you truncate the entire domain, right? And then we go to the scientist's hypothesis and say, well, what happens if we don't truncate the center of domain? We only truncate these coarser grid cells. And then you can look at this next step where all we do is just leave out these finest grid cells. Everything else gets truncated. And suddenly our truncation error improves significantly. So in this case, we can go all the way down to FP32 and only lose 2 errors of magnitude. And depending on what the domain scientist needs, whatever their goals might be for this experiment, they might even say, well, we can go down to FP16 because it's still lower than 10 to the minus 8 error. And maybe for qualitative experiments, this is good enough. And then we can truncate even less, kind of go to only even coarser cells. But in that case, nothing much happens. But then the interesting part would be to test this also on a different case, right? So we can test it on this SOD shock. Which essentially have a low pressure region and a high pressure region which are separated by a membrane. You pop that membrane and then you get shock waves propagating in one direction and kind of rarefaction waves propagating in the other direction. And you can also already start to see it here, kind of the effects of this where you need fine grid cells are a lot more distributed across the domain. And also just because of how the fluid dynamic problem works is you just have interesting effects happening all over the domain in more places. And as it turns out, if you try to use the same strategy and only truncate coarse grid cells, you notice that, well, this doesn't really improve accuracy much. So your truncation error kind of stays the same whether you look at the left side or the right side here. Simply because there's more physics happening all over the domain, so this strategy doesn't work as well. But this does kind of show that the domain scientist hypothesis was correct, that in areas where there's no interesting physics happening, you can truncate your simulation and it's fine. So all of this was just Raptor op mode, but we can do a lot more. So remember, op mode truncates after every operation and then expands back to full precision. Well, we have something called mem mode, which doesn't truncate and expand every time. And this means that we need to actually store an arbitrary struct for every floating point value and variable that occurs in your code, which is not super trivial because you can have an array of floating point values, and it's not so easy to track where that data is going. But Raptor can do this by jumping through a few hoops. And what this means is that we have this arbitrary struct. We can store any information in there, and that means we can start diagnosing operations individually and measuring things individually, and kind of trace and pinpoint problems as they occur in the program execution. So the really simple mental model to have here is to say, well, I have some kind of trace of floating point operations. Let's truncate those to FP16 and see what happens. And at the same time, we can run kind of a trace of FP64 operations and compare the two. And then we can ask, well, if we look at this operation in line 13, did FP16 drift at all? Where did it drift? Maybe it didn't drift at line 13, maybe it drifted earlier. Raptor could tell you about this. And you can kind of start figuring out maybe where are problematic regions in this code. Maybe line 13 has some super bad cancellation happening. This is all nice and good. It would be wonderful if it works. Unfortunately, this is a bit of an oversimplification, so we tried this. And it's not quite this simple, but that's good news for me because that means I get more research to do for my PhD. And in this final part of the presentation, I want to kind of show why I think this is still the way to go to do these experiments. So mem mode is still very powerful simply because it allows us to implement our own kind of metrics. So I want to just pitch a few ideas. So one thing you could do is if you, again, have some trace of arbitrary computations, you could use bisection to automatically find which operations are fine and which operations might be problematic in low precision. So essentially just start by truncating everything. You get a wrong result. Maybe it just explodes or it deviates from your reference. So you try again by just truncating the first half. Still explodes. Let's try the other half. Maybe this one works. We get a correct result. However, this is not yet the full amount of operations that you could truncate in here without getting problems. So you can kind of keep iterating and trying different subsets of this. And finally, in the end, you might get a very specific configuration where you're truncating exactly these lines, and you know that it's impossible to truncate more without breaking a result. And then this is kind of your solution to this. And then a performance engineer or domain scientist or whoever is looking at this can then use this information to kind of figure out where are the areas in my code that I might need to spend a bit more time on to fix issues. And this you could do with op mode in theory, but in mem mode you could, again, measure additional metrics to help you guide this kind of diagnosis. Sorry. Right, then to the second idea. I've already hinted at this. You can do multiple precision streams at the same time with mem mode. You have this arbitrary struct, so you can store whatever you want in there, and you can do whatever operations you want in there. You don't have to just do the operation that was prescribed by the code. So what you could do, conceptually, is have an FP16 stream and FP32 stream, run both of those, and check how the FP16 deviates at each operation, and maybe at some point it crashes, so it turns into a NaN, or it just deviates more from the FP32 than you want it to. And in op mode, you would kind of just be stuck at that point. You just have to maybe try with a higher precision and see what's going on. In mem mode, you could just run the simultaneous FP32 stream and just restart your FP16. So then, sure, you will see kind of where FP16 has crashed, and this won't necessarily tell you the lines in your program that are tricky for low precision, but it will give you a better idea of, well, here things are running fine, and then here suddenly I kind of start getting a lot of problems. And then you can also kind of continue this idea and see that FP32 might also crash. Well, just add another stream. Just simulate this thing or run this thing with a number of precisions at the same time in kind of lockstep. And then you can just restart FP32 from this point. And since we're using MPFR, which really supports arbitrary precision, nothing's stopping you from using something crazy like FP2048 and just running that as a kind of ground truth reference. And who knows, maybe in the end you figure out that FP64 is also actually doing things that I didn't expect it to do and don't want it to do. Right. So the takeaway from this is that with mem mode, you can really compare step for step, and it also allows you to implement whatever measurements you might be interested in. And I think the really interesting research part of this that I don't have solutions for yet, but I think will be very interesting to look into, is finding out what exactly we want to measure at these points. And I really want you to think about this as a kind of profiler. So usually you have a profiler that tells you where your application is performing badly. In this case, we want to have a profiler which doesn't look at performance, but it looks at FP floating point accuracy and tells you where your application is performing poorly under low precision or under truncation. Right. So that gets me to the conclusion. Yeah, Raptor is a tool for numerical profiling experimentation. You can use it on CPU and GPU, and you can figure out if or whether scientific applications written with FP64 can tolerate lower precisions. And as it turns out, that works sometimes. I also have this figure which I didn't really go into more detail, but this is also another experiment we did with this kind of rising bubble in water, and you can also see how the results kind of qualitatively diverge from the FP64 result. The QR code gets you to this link, so that's the source code. We did win the reproducibility award for our paper, so I'm pretty confident that if you check out the appendix, you'll be able to reproduce these results with the shockwave and the SOD problem. And otherwise, I would be super happy to talk to you if you want to try using Raptor for your own scientific application, because I think the way this will evolve is really going to be in collaboration with domain scientists who can kind of point out the interesting parts of the code to apply this to. Thank you.
Thank you, Faveo. Any questions?
Hi, thanks for the presentation. I like your approach to use lower precision, mixed precision. However, I believe the comparison on slide number 2 was not correct because you are comparing Hopper with Blackwell Ultra. Blackwell Ultra is a pure AI GPU, and this comparison gives the impression that NVIDIA does not support any double precision in the future, which is not true. So Blackwell Ultra, the B300, does not support double precision as it is an AI GPU. The B200 Blackwell and also the following GPU generations, Ruby and Feynman, will support the double precision, and one has to distinct between the vector and the tensor core units, of course, right? Yes. So we have removed the tensor cores for the DGEM operations, therefore we are using the emulation, so a lot of things going on, collaboration, development on the emulation. So NVIDIA will support also in the future double precision vector units.
Yes,
thank you.
Thanks for the comment. I did expect this slide to land me in some hot water, but it's good because that kind of drives the discussion. And again, I think I'm happy that I made the second point, which is that, well, even if we still do have continued FP64 support, we have this amazing performance in lower precisions, and it would be nice if we can exploit that for scientific simulations. So even if we continue to have amazing FP64, why not diversify and make use of mixed precision? Thanks.
Sorry, who had the question here?
Yeah. This looks really interesting, especially with the kind of bisection for finding the optimal numerical precision. I was wondering, I have a very nasty legacy code base for some gravity calculations. I wonder how much out of the box can I apply your strategies.
What did you say was the code?
It's a gravity solver for n-body simulations.
Got it. So in principle, even without writing or without changing any code, you can use this. Okay, it's pointless for me to try to find that slide. You can use this kind of full program truncation to just see what happens. And at that point, the way you use Raptor is you just write function wrappers, or you wrap the functions that you want to truncate. So in principle, it should be usable out of the box. As a disclaimer, I worked on something else for my master thesis, so essentially for the last year, I haven't been able to really touch and maintain Raptor at all. But I'm going to start my PhD in fall, and then I'm looking forward to kind of maintaining it and really also supporting users. But maybe we can also look at this offline, and it would be really interesting to see if we can use this.
One last question.
Thank you for the nice talk. You showed a couple of examples, the shock wave, the wavefront, and also the bubble at the end.
Yes.
I would guess that if you look for the same application with different inputs, with maybe a little bit different science that you simulate, that all of your changes to the accuracy, they will differ. So do you, I'm not looking for anything where you say this is the solution, but do you have any idea on how to tackle that? So maybe look at different offsets for different inputs, because if for every input you need to change your whole precision flow throughout your whole application, that will be a big bottleneck, I guess.
I'm not sure I fully understand your question. Yes.
So maybe I can formulate it differently.
Mm-hmm.
If you look at simulation software, they can run with different inputs. You can simulate different things, and you might have different scales. And with different scales, you will get different offsets in your accuracy. So you might have two very large numbers or very small numbers, and then mix and match them. Yes. So your differences will be different for different inputs for the same application. Do you have any idea how to deal with that?
I think, well, of course, what you can do, first of all, is just run an ensemble of applications and essentially just put error bars around your execution. And it's actually funny that you point this out, because you see this interesting effect here where for low precisions, you suddenly get an increase in accuracy. And in this case, this is kind of parallel to what you were saying, because here the adaptive mesh refinement is just not happy with the results on these coarse cells. So it refines all of them, and then suddenly this M-2 case has no more cells to truncate. So the adaptive mesh refinement is actually causing something similar to what you're saying, where the results actually subtly change. I think for one, with op mode, in this case, you can just run, you can just sample your space and see what happens. And you will, I think, quickly see if this is sensitive or not. And I think if it is sensitive, then this is a sign that maybe this is exactly where you're having problems, because with very slightly different inputs, you're suddenly getting big variations in accuracy. And second of all, what you can do again with mem modes, so similar to this idea of running multiple precisions at the same time, you could also change all of this into, let's say, FP32 and perturb the results slightly. So you don't just need to do you couldn't just do an ensemble of simulations kind of in the classical sense, in the way that weather simulations do. They just perturb results and run like 100 simulations and then do statistics on that. You could actually do all of this at the same time and do statistics on this while it's running. And then maybe, this is going far beyond like my kind of core knowledge, but I think you might even be able to do something like Bayesian sampling and say, while the program is running, we're not actually getting results in this area. Maybe let's try to start a few additional calculation streams here to try to sample this full space of possible deviations that we might get from the reference. So yeah, thanks for pointing that out. That gave me a nice idea.
Thank you, Faveo.
Thanks.